Good afternoon to all the dignitaries present here. Welcome to this emission monitoring and circular economy practices. We have with us an esteemed panel. As we go along, I will welcome each and everyone and then will not waste much time on the introduction. We have with us first Dr. Gurleen Kaur from International Solar Alliance. She will be speaking about Indian solar PV waste challenge and will be enlightening us how to manage it, how the recycling hubs for a circular economy can be taken forward. Over to you, madam. Thank you.
A very good afternoon, everyone, and thank you for being here at India Energy Week. As we know, India today is in the middle of one of the most exciting clean energy stories anywhere in the world. As of 2025, we have crossed around 123 gigawatts of installed solar capacity, making India the fifth largest solar nation globally. And that is a remarkable feat, my dear friends. But I want to start with a slightly uncomfortable but necessary question, which is what happens when all these solar assets retire? Because panels don't disappear politely. They don't walk off the stage like tired actors or me after this talk. They stay. And if we don't plan properly, India's solar revolution could end up in landfills, like most of the electronic waste that we are dealing with now. And right now, in the stage of sustainable economy, circular practices, India being a champion of that, we don't want that. So this presentation will examine India's emerging PV waste challenge, the policy gaps, and data-driven pathways towards regional recycling hubs that can anchor circular economies. Very quickly, I represent International Solar Alliance, which is a coalition of 124 member countries created to accelerate clean energy globally. And which brings us to the new platform that ISA has launched, which is Sunrise. It is the solar upcycling network for recycling, innovation, and stakeholder engagement. And through our means, our goal is to build over 200 community of practice members by 2028, connecting governments, industry, and academia. So we are here to enable change and enable our member countries to design, deploy, and recover solar components responsibly. So globally, we have installed around, this is all data, not 186 terawatt, but around 2.2 terawatts of energy. And by 2049, this will become 124 million tons of waste according to ISA's estimates. And as I like to say, this would be 114 Mount Everest placed next to each other, all made up of solar panels, which is very impressive, but at the same time, very terrifying. So PV waste is not just a trash, but it is a multi-resource stream. Silicon, silver, aluminium results in a multi-billion-dollar industries when recovered annually in terms of these materials. And in this case, the driver is not just environmental sustainability, but also it is a very strategic mineral security. So now let's move to India, where we can see how things can get real. As I've already mentioned, India's growth story is extraordinary. A 43-fold increase in just 12 years. It's like going from a cycle to bullet train just in one decade. But here is the consequence. Solar success creates solar responsibility because every panel we install today, as I mentioned, will eventually retire. And when it does, it becomes part of the next big challenge. So while the PV waste are still manageable challenge today, the window that we have here is to prepare for future when the waste starts piling up. So this study that I'm going to present will focus on three things. The first one is to quantify PV waste generation challenge state by state in India. Number two, highlighting the policy vacuum in India's regulation. And number three, proposing a solution, which would be development of regional recycling and resource recovery hubs. So based on our analysis, PV waste will not be evenly distributed throughout the country. It is going to be highly concentrated, and the top 5 states will dominate, which are Rajasthan, Gujarat, Maharashtra, Karnataka, and Tamil Nadu. Together, they will generate over 55% of India's future solar waste. And here is the scale of the challenge. India is projected to generate 444 kilotons of PV waste annually by 2049 and a cumulative stock of 6.4 million metric tons. It would be as big as the Great Pyramid of Giza. And that is not a future problem, but that is the future certainty, because these modules are already on field and they will face the end of life after 25 years. So the question once again would be, will we build infrastructure before the waste arrives or after it arrives in someone's backyard or landfills? So this is why long-term recycling planning is urgent. And in India, the PV waste is not one single waste stream. It will come from utility scale solar parks, rooftop systems, off-grid rural applications, which means some waste is concentrated, some waste is going to be dispersed, and at the same time, some waste will have logistically complex managing challenges. So just to give you an analogy, that managing this waste would be like managing traffic problems in India. So one rule will not apply for side lanes or highways. So different sorts of mechanisms will have to be created for different kinds of waste streams. And when we look at the policy challenge or the governance challenge, India currently does not have a clear state-specific PV waste rules. Solar modules do fall under the e-waste regulations, but the producers are exempt from binding recycling targets, enforcement is unclear, state-level implementation is missing. We have CPCB guidelines, draft guidelines from June of 2025, but the reality is that we still have a policy gap right now. And waste doesn't wait for policy to catch up. So what do we propose? We propose a hub and cluster model with regional recycling hubs. Why? Because PV waste is heterogeneous, as I mentioned. Uniform centralization is neither scalable nor economical or resilient. So the 3 principles that will guide this recycling hub design would be regional proximity to highway streams, system-specific process capability, scalability over time aligned with waste growth trajectories. This will ensure flexibility, efficiency, and long-term viability. So as per our analysis, the first wave of hubs should begin where the waste is highest and the infrastructure is ready. Rajasthan, highest projected waste volumes, can be the utility scale anchor, followed by Gujarat, which has a strong industry and logistics access. Phase 2 in a few years would expand into Maharashtra, Karnataka, Tamil Nadu, and these states can be innovation and distributed waste hubs. And third phase would build capacity in the east and work on developing the future hubs, or we can say future proofing the solar in the east. And they will have hubs in Odisha or West Bengal. So early investments in all this infrastructure in different regions of the country will help prevent long-term environment and economic liabilities. But what will these hubs exactly do? these hubs will actually become an ecosystem where there will be collection, dismantling, recycling, as well as material recovery. And all of this will cyclically go back to development of the new panels from the old silicon. To conclude, India's solar transition cannot remain linear, which is manufacture, deploy, and discard. To align with net zero, resource efficiency, and energy security, we must recover critical materials, reduce reliance on virgin imports, prevent environment degradation. Circularity is not a cost burden. It is a strategic investment opportunity, not in the interest of our country, but also in the interest of the entire industry and infrastructure cost that we are adding to as well. So the opportunity that Sunrise through ISA seeks to unlock is a global leadership position for India in circular solar economies. With the right regional hubs, harmonized policies, industry participation, we can turn a looming waste challenge into a sustainable economic engine. Thank you.
Thank you, Dr. Gurleen. Now, I'd like to invite Dr. Sneha R Iyer from Tata Consulting Engineers to tell us about the integrated silicon value chain for solar photovoltaic cells, talking about energy and material recovery.
Thank you for the kind introduction. I would like to thank the organizers of IEW and the management of Tata Consulting Engineers to have given me this opportunity to be part of India Energy Week and present on the topic, which is gaining quite traction in India at present. That is the integrated silicon value chain for solar photovoltaics. And how it can be achieved through material and energy recovery. So I'll be talking about the entire silicon value chain. So the foundational material for your solar photovoltaics and your semiconductors is silicon. So where does this silicon come from? It comes from a mine called quartzite, and it comprises of majorly silicon oxide and silicon oxide. It undergoes carbothermic reduction to form metallurgical grade silicon. So you have to convert silicon oxide into pure form of silicon in order to make it usable for your electronics as well as photovoltaic application. So these steps goes as quartzite is converted. So as I was saying, silicon is the foundational material in the process for solar photovoltaics as well as semiconductors. So the starting material being quartz. So the quartz comprises of silicon oxide. It has to be purified to ultra pure quality in order to be used in your photovoltaics as well as semiconductor devices. So if you see, there are multiple steps in which silicon is purified. The first one being the conversion of quartzite into metallurgical grade silicon, which is more than 99% pure silicon. Afterwards, it undergoes through Siemens process to produce polysilicon. So in polysilicon, its purity is close to 9 to 11 N. So it's like 99.99. So after the decimals, total 9 N. So after polysilicon, it undergoes Czochralski crystal growth. This is a monocrystalline silicon ingot that is pulled, and later on the wafers are sliced. From this, the bifurcation happens. That is, it goes through either electronics or the solar photovoltaics, depending on its purity. So in this entire value chain, you have multiple byproducts that are occurring. So from the quartzite stage, so you have quartzite being used for glass, for solar, for refractory materials, silicones, ferrosilicones, silicon tetrachloride for quartz crucible. Then you have silane gas, which is used for PECVD process for both solar as well as photovoltaic chips. Then the silicon kerf that is processed can also be recycled, which we'll see in the upcoming slides, as well as battery materials. So this is the entire silicon value chain that comprises of silicon and its byproducts. So what we have proposed is a complete holistic approach of energy and material recovery. So if you see the first orange block, that is the energy recovery process. So in your carbothermic reduction, you have off gases that are generated of very high temperature. So this high temperature off gases can be used to run certain reactions which are there in the polysilicon process. So polysilicon process has two major steps. If you see, it has hydrochlorination as well as cold hydrogenation. So your metallurgical grade silicon needs to be gasified and converted into a gaseous chlorosilane form. This chlorosilane gas purity is also quite critical. Once you get the chlorosilane gas, it is purified. And you have many of the off gases that are generated that needs to be converted back into this desired chlorosilane. So TCS is nothing but trichlorosilane. So we have abbreviated it for getting the entire stuff into one slide. And in the cold hydrogenation process, this is endothermic process. So endothermic process actually demands energy. It requires heating utilities. So in order to maintain the reaction temperature, we use these off gases which can actually drive this cold hydrogenation process, which converts your undesired gaseous material into trichlorosilane. This is a precursor for your purest form of silicon. Once we get this trichlorosilane, it undergoes Siemens chemical reposition process, which is a bell jar kind of a reactor, which requires huge amount of electricity and it is highly energy intensive. So in this process, your polysilicon which is deposited, it has a purity of 9 to 11 N. Later on, we move on to the ingot pulling process. Afterwards, we slice this ingot into wafers. Slice these ingot into wafers. The kerf that is generated, it can be purified, passivated, mixed, pelletized, and then sent back to the metallurgical grade silicon. Now, why we are purifying this kerf is because this kerf is already a pure form of silicon, which has gone through all these process steps which are highly energy intensive. So in order to salvage that kerf material which is already in pure form, we recycle it back into the polysilicon process. Now it cannot be directly recycled. We'll see how we recycle in the upcoming slides. So we need some mass and energy balance to understand how this system is going to work as a whole. So we look at some of the consumption quantities of the raw materials of MG silicon, what kind of coal quantities are required, wood chips required, the quartz quantities required. And based on this, we calculate the stoichiometry. Based on the stoichiometry, we calculate how much of the exhaust gas is going to be generated, and from that exhaust gas, how much is the energy that we are going to get. So moving on to polysilicon to wafer, this we have assumed that the CVD reactor that we have will have around 20,000 metric tons per annum of production capacity. There will be multiple configurations of this rod and the CVD reactor type, as well as the run time. Based on that, we have come up with the numbers. Again, ingot and wafer puller yields are also assumed. The waste that is going to be generated through the ingot Czochralski crystal growth process, that we have around 2% loss. And in the wafer slicing stage, we have 40% loss. This gives us a fair idea that what is the amount of waste and what is the amount of silicon waste that is going to be generated, as well as the waste heat or the energy that is going to be generated through off gases. So we split it into two parts. First part is the heat integration. In heat integration, we have two major sources of energy intensive process, that is your submerged arc furnace as well as the Siemens CVD reactor. So these in these units you have reactions in the order of thousands to 1200 degrees centigrade. So the exhaust gases which are generated are around 400 to 800 degrees centigrade. This can be used to run your cold hydrogenation reaction, which is which requires temperature to be maintained at around 300 to 600 degrees centigrade. So this exhaust gases can heat the thermal fluid to maintain this reaction temperature. So this is one part. Another part is the Siemens CVD reactor, where you try to generate steam. This steam is superheated because now after exchanging energy with the thermal fluid, it still has substantial residual amount of energy to be taken up So in the subsequent heat exchanges, we try to superheat the steam as well as we try to preheat the feed required for steam generation. So this is the entire heat integration process that we had worked out. There may be multiple permutation and combinations for these. This is one of them. Next, moving on to the material integration part, we look at where and all the silicon solid wastes are occurring. So in the CVD post-handling process, in TCS synthesis and purification process, where you have particulate matter that is generated and cannot be used directly, those materials are collected. From the diamond wire sawing, you have kerf losses. So all these particulate matters are in the order of 100 microns. These cannot be directly used in your metallurgical grade silicon process. You need to process them, purify them, and you have to increase their size, because mostly the chunks are of size of 40 mm. From micron to 40 mm, you'll have to mix, pelletize, and then again recycle it back. So in this entire value chain or the heat and material integration that we have done, the energy consumption for the required metallurgical grade silicon, it has come down from 20 kilowatt hour per kg of metallurgical grade silicon, which is the conventional process without recycle. It goes down to 16 kilowatt hour. So how this is happening is because you have an additional capacity. So the additional capacity that is generated is around 9,000 metric tons per annum. This additional capacity is added to the original capex of the material. That is around original envisaged design of the plant, that is around 38,000 metric tons per annum. So 38,000 metric tons per annum is what is required for your 20,000 metric tons per annum of CVD reactor that we had seen in the previous slide. So without taking much time, the key takeaways would be that if you have a combined integrated quartz to wafer strategy, your energy and material recovery becomes much more efficient, and also your waste heat recovery remains within the system, and it can be used to reduce your auxiliary energy requirements. Also, this closed loop design increases your TCS conversion yield to 31%. Conventionally, it is around 25 to 27%. So overall impact would be that an energy efficient as well as reduced waste improves the material utilization as well as the energy recovery in this process. And because of this, most of your backward integration systems become commercially viable as we move ahead towards the ingot wafer as well as the polysilicon process. Till now in India, we have gone through modules and cells. Slowly we are going behind. So this becomes a topic of relevance. So with this, I would like to conclude. Thank you so much.
Thank you, Dr. Sneha, for explaining the entire process. Now I'd like to invite Mr. Satyanarayan Mahapatra from Adani New Industries Limited, who will explain us about recovery of critical metals from end-of-life solar PV products. Over to you, Mr. Satyanarayan.
Thank you. Thank you, Mr. Dibyendu. First of all, I'm very grateful to India Energy Week organizers for this opportunity, as well as to the Adani team to showcase. Initially, I was very much worried that the 2 years of entire R&D which we have been doing for the recovery of critical metals, how I can explain in 15 minutes. But both my previous speakers, Dr. Gurleen and Dr. Sneha, has already set up the context that how it is important for the creation of a circular economy for the entire solar industry. As of now, we have already more than 100 gigawatt of solar manufacturing, module manufacturing in India, and if I say Adani is building a 10 gigawatt of complete value chain of solar manufacturing in Mundra in Gujarat. So this is basically a project which we have been doing along with IIT Bombay to how to recover, the critical metals like silicon, to manufacture silicon anode material, which is used for battery manufacturing. So if you ask me, like, what are the major challenges in terms of this? So one is, of course, the recovery of the material, because in India we always term any waste as a scrap. So first of all, we have to remove that mindset of scrap. So particularly in solar PV manufacturing, nothing is called scrap. It is basically the byproducts which comes out of the manufacturing, which is not usable. So it is duty of organizations like the large manufacturers like Adani, Reliance, Tata, who are setting up the huge manufacturing to recycle this material. Okay, so now moving to the topic where we are basically doing a study to analyze the performance of silicon which is being generated from the wafering plant. So we have a 2 gigawatt of ingot and wafer manufacturing setup in Adani. We are being the first manufacturers of ingot and wafer in the country. So where we are basically producing about 4 metric ton of silicon curve in the solar manufacturing, which is not being used back in the process till we set up a MG poly manufacturing. So in this, basically we are processing this curve to generate an anode material for lithium ion battery manufacturing, to study the material characteristic and how we can economically remove the organic and inorganic impurity present in this curve through the analysis. So first, there is a organic impurity removal, which is being heated when we heated it at a 700-degree temperature. First, we were able to remove the organic impurity. Is basically the coolant which is used in the wafer slicing process is organic material which get added to this silicon curve material, and that get removed at 700-degree temperature. And when we did the complete analysis of this curve, so there are basically 4 types of different curve samples were used. One is the fresh filter press curve, where we are processing the silicon curve from the wafering plant, then the vacuum filtered silicon curve, then the filter press silicon curve dried at almost like 120 degrees Celsius for about 2 hours, then the vacuum filtered curve which is calcined and heated at a temperature in an inert atmosphere for about 700 degrees Celsius. So this is the entire process of organic impurity removal, where the TG and DT analysis was conducted and the curve sample was removed. So in the organic impurity removal for the filter press silicon curve, first filter press silicon curve is passed through the TD peak higher than low TD and high TD peak volume, and the silicon oxide and the moisture which was being presented, that is through the one spectral range, that was removed, and the organic peaks are we found that is low due to low mass filtration, and hydrocarbon and other organic impurities which were present that start disappear, showing decomposition of hydrocarbons. So if you look at the particle morphology at the 4 sample curve which we processed at a induction furnace through an inert atmosphere, we found the material characteristics of different curve at different temperature and atmosphere, and this is the bulk material chemical composition which we found in the silicon curve. So the majority of critical metals which was present is the silicon, which is almost about 90%, and the second most prominent was the Fe. Basically, we use a carbon steel and diamond coated wire used, almost like 32 micron diamond wire is used for cutting the bricks to manufacture the wafers. That was the second most prominent. so these were the bulk composition. Then there was a centrifugal trial which was taken, and the electrode composition for the electrode silicon electrode composition, there was a separate sample was prepared, and out of that the anode material which is used 99% pure silicon powder that was being recovered through this process. So maybe the organizers, they can share the presentation later on. There are some technical glitches. So this is how the silicon electrode was prepared, where the active material was the fresh silicon curve, and the conducting medium was the carbon black, and a binder which was used as a sodium agnate, and solvent was the DI water. So in the method, first 20-minute dry grinding was conducted using a mortar pestle, then 20-minute dry mixing with a slurry mixture, and then 45-minute wet mixing were done using adding the DI water. So as it appeared, there was no proper mixing of silicon curve and carbon black was done in the slurry mixture, and it was later it was planned to do some hand grinding and for the electrode preparation by using hamper specific capacity of the material. So if I summarize the entire study, so first the organic impurities, they were removed, which was present in the silicon curve between the temperature range of 620 degrees centigrade, and both type of curve, like we got the flake morphology, and this curve was being highly agglomerated with the particle size, varying different particle size. So we have processed this into crystal structure, amorphous silicon, and which was later produced for the recovering the critical silicon metal out of that. So right now we have collaborated with a Norwegian company called Resitec for the technological partnership, who are like providing us the technology to prepare the anode material, and we have also made collaboration with Hyderabad based research lab called ARCI, who are helping us to prepare the binders and meta alloys which can be used for usage of this curve, which is not being used for the anode material for the different application. Let's say for the manufacturing of the other aluminum meta alloys, as well as the ferrosilicon which is used in the steel industry, as well as the refractory material. So from the waste silicon curve, we are now able to manufacture different byproducts, including the battery material and the other byproducts which are used for the different industry. So this is how we are currently working to reuse this silicon curve for the different industries. And as we move forward, when we will set up the MGSI factory in the next 2 years, then we will be back using this silicon material which is being recovered for the production of polysilicon, and use it for again back in the ingot and wafer manufacturing. So that's all from my side. Thank you.
Thank you, Mr. Satyanarayan, for your nice presentation. And I liked your comment about thinking that there should be no scrap in the process. So now I'd like to invite Mr. Karthick from Mangalore Refinery and Petrochemicals, who will talk about depolymerization of circular plastic and also about a demonstration government-funded indigenous PET plastic chemical recycling technology. Over to you, Mr. Karthik.
Very good morning. So I understand I'm standing between you and your lunch, so I will keep it as fast as possible. So I am from Mangalore Refinery and Petrochemical Limited, which is a downstream arm of ONGC, and I belong to Innovation Center team, which is the R&D section of MRPL, and we focus on two main areas. One, we are developing our patented closed loop real-time optimizer softwares to improve our productivity as well as reliability, and we are also focusing on futuristic process technology like active pharma intermediates. We have developed our own technology which makes brufen as well as paracetamol as well as aspirin, the intermediates for that, we are also focusing on net zero related CCUS as well as plastic circularity technologies. So with this, I'll just, we are very late to start. We started the R&D way back in 2018 and we got, as on date, about 35 patents, out of which 4 international, and we got actually 6 innovations, the patent innovations commercialized already, 2 are under commercialization, and for the last 4 years, we won back-to-back innovation award from Government of India. So coming to the topic, I mean plastic waste. For our country, it is a very, very pertinent area. Why? Because we are the largest plastic polluter, plastic waste emission across the globe. About 9.3 million tons of plastic is already emitted. This is a last year study in Nature. Though we are not the biggest producer of plastic, though we are the third largest plastic producer, but we are the largest plastic waste emitter. That is mainly because of uncontrolled disposition of particles and mismanagement of the waste collection. So we understand why it is very important to the country, and globally there is a lot of action stacking on the plastic waste. Similar to COP21, there is a global plastic treaty that is under the anvil. This is supposed to be completed by 2024, a legally binding instrument. As a law, 193 countries across the globe are supposed to pass, preventing the plastic waste. This covers the entire life cycle of plastic, right from generation till usage, disposal and the recycling. Unfortunately, few countries are preventing this treaty to be concluded. Mainly the bone of contention is there is a clause which prevents the fresh production of plastic. So many of the oil producing countries are against this. So that is the reason why the treaty is not yet signed. But the expected conclusion is right now in 2026 it is expected to be completed. Mainly, instead of building a consensus, it is expected that the treaty will go for a voting phase. So about a few countries which are not for this plastic treaty may be voted out, and if that happens by 2027-28, there will be a nationally action plan which will be passed as law in all the countries. So mainly this is going to actually mandate a very good actually recycling of plastics. It is going to reduce fresh production of plastics, and not only that, chemical recycling of plastic technologies. There is going to be a lot of focus on that because virgin plastic is going to be under stress. There is going to be a roadmap to reduce virgin plastic make. Though the plastic consumption is increasing, that is going to be more of from the recycled plastic. So basically this plastic is not against, this law is not against petrochemicals. It is the way we are producing the plastic that is going to get changed. And Government of India is also little, if you say they are not waiting for this law, they are little proactive. The extended producer responsibility law. This is also already announced, and there are various mandates till 27-28, which is going to increase the plastic circularity. They are categorizing the plastic basically into 3: rigid plastics, which are used for packaging, as well as plastic actually buckets or other plastic furniture also. Flexible plastic, this is used widely in plastic covering, packaging, and multi-layer plastic, this is used in biscuit packing, milk packing, and food plastics, food packaging. So basically flexible plastics and MLP, multi-layer plastic, are very difficult to recycle. There is a roadmap which is as not stringent as rigid plastic. Whereas in case of rigid plastic, mainly our plastic bottles like PET plastics, as well as polypropylene based actually utensils or plastic wares, these are going to have a very high recycle targets. Already this year we are supposed to recycle 30% of rigid plastic which is used in packaging, whereas which is used in manufacturing, there is a target of 50%. The manufacturing target goes as high as 80% up to 27-28 in rigid plastic, whereas the packaging guys has to use at least 60% by 28-29. The challenge here is, though this is very, very ambitious, the technology arena is not in place. Already there is a lot of protest from the plastic manufacturers as well as packaging industry against this mandate. Basically, if you take PET plastic, which is used for the bottles, once used bottles which we use for drinking, up to 30 or 50%, 30 to 50%, there is only mechanical recycling. So as you increase the number of cycles, the plastic quality deteriorates. It becomes hazy. The physical properties to blow it to make the bottles again is very, very difficult. So what typically people do is they take the bottles, they convert into PET fibers. So this is pretty much established in mechanical recycling. It is kind of downcycling, but still the PET fibers can be used as fabrics. So up to 50% to a certain extent this can be managed. But the challenge lies beyond that. When it is 60% in packaging or 80%, 60% for flexible plastics, it's very difficult unless the technology evolves. So this is a state of plastic recycling as on date. The left side graph that gives kind of actually what is the status. This is a McKinsey study. So this gives, if you look at about 90%, it says it is dumped on the whereas where we are today is only 12% mechanical recycling. So this is a challenge. About 25% is incinerated and 40% is put in landfill. Whereas as I told earlier, the mandate is to go up to 60% recycling for producer, whereas if it is a user, it has to go high as 80%. And in terms of the real circularity, incineration, what happens today, it still emits 80% carbon. Whereas this is what most of the waste recycling facilities is doing today. They are going for incineration with energy recycling and landfill. These are a very 50 to 30% carbon emission. What even mechanical recycling or pyrolysis. Pyrolysis is what everybody is trying to do today when we speak of chemical recycling. Unfortunately, it is not a truly circular technology. There is only one cycle, hardly 10 or 44% the molecules are recycled back, whereas rest ends up as fuel. And this fuel doesn't have carbon intensity. So what is really desired is chemically recycling back what is called as solvolysis or dissolution and precipitation. So this is a technology which is truly circular technology, and this is what we are trying to do. So coming back to the topic, we have developed a wide portfolio of chemical recycling technologies. The one which I am going to cover in detail is PET, that is polyethyl terephthalate, which is used for bottle recycling. Also the fabrics. Today there is no technology for even fabric recycling. Bottle at least downgraded to get fabric, but fabric there is very few technologies. And MLP today there is no technology. It is getting incinerated or it is going to a cement industry. We have a technology which we chemically recycle the multi-layer plastics as well as blister packets. Blister packets are nothing but your pharmaceutical packaging. And then we also have the rest of the plastics, be it polypropylene, polyethylene or polycarbonate. We chemically recycle to their monomer. This is the technology portfolio we have today. So I will focus today right now on the PET. Excuse me, the slide is not navigating. Yeah, thank you. To understand the depolymerization, I just want to touch how it is polymerized today. So basically what we do is there are two wide roads. You can take purified terephthalic acid, PTA, and recycle, and along with ethylene glycol, we produce this 2-hydroxyethyl terephthalate. This is the building block. Either you come from purified terephthalic acid or you come from dimethyl terephthalate. Along with ethylene glycol, it forms, both forms BHET, this hydroxy to ethyl terephthalate. This ultimately polymerized to form PET. So this PET has to depolymerize back to either TPA or BHET. Most of the technologies focus on TPA. So there are widely 5 different processes. Ultimately, either people try to make amide form of BHET or they try to make TPA. There are some technologies which make BHET. Unfortunately, you can at the right side you can look at what is being scaled up. Most of them are ending up at terephthalic acid. Only there is one technology which is trying to look at BHET, and there is rest are all looking at TPA. The issue today is TPA. When they make TPA, EG is getting lost. They cannot recover the ethylene glycol. They only recover one part of the cycle, whereas the BHET is widely the better route, but unfortunately it is a catalytic process and not that efficient. It is a very costly process, and we try to actually, it is not viable on its own without any viability gap funding. So what we have did is, it's a very competitive process. Our process doesn't have any catalytic involved at all. There is no catalyst. It is very mild. The temperature is less than 200 degree. The most actually path breaking part is we make 99% of DHET. Today this level of recovery nobody has. This level of depolymerization, everybody hardly tries to make 60 to 70% of DHET. There is also oligomer of DHET. There is no breaking that to BHET yet, but we are getting 99%. And looking at the merit of this process, Government of India through OADP, Center for Higher Technology and OADP, they have funded 50% of this plant cost to scale up to pilot cum demo plant level. We are right now at this level, and you can see this technologies that is right now getting built. So what we do here is we try to revalidate the batch plant parameters here. We try to look at various type of weeds, right from bottle, right from fabrics, how the technology performs at a continuous plant level. We try to look at various impact of recycles. Certain solvents which is used in this process are getting recycled. So continuous evaluation of this recycles. We try to optimize the process also by try to look at actually how much can be recycled, how much has to be purged, how much fresh has to be made up, and downstream separation. Basically the monomer is crystallized back. The number of crystallization so that it meets the virgin polymer quality. So this downstream separation is also being studied at this stage. We are right now at this stage. So this by April 2026, this plant is expected to be commissioned. So subsequently by next financial year, once the parametric studies, as I mentioned earlier, are completed, in a matter of about 6 months, we intend to carry out basic engineering design for commercial scale, and a matter of 2 years, subject to all approvals as well as demonstration of the process, we intend to go towards commercialization by 2029. We are also working with various partners and collaborators across the value chain, right from plastic aggregators, and then downstream once we depolymerize, there are players who polymerize back to again PET. We are collaborating with them. So by 2029, we intend to do all this and successfully commercialize this. We are at the technology readiness level of TRL 7 today. We intend to go to TRL 9 by 2029. Thank you very much. So I'm eager to listen for the query subsequently if there is time. Thank you.
Thank you, Mr. Karthik. Now I'd like to invite Shri Prakash Chand Sharma from NHPC, who will tell us about circular economic practices in hydro and renewable energy. Over to you, sir.
Thank you, sir, for this kind introduction. Respected session judge, fellow panelists, and all the industry colleagues present over here. My name is Prakash, and I am from NHPC, and I am thankful to NHPC and IEW to be a part of this great event. Our organization NHPC is working in hydro and renewable sectors, and we are one of the largest green and clean power of country. So our NHPC Limited is one of the largest green and clean power of India. We are having about 23 operational power plants, contributing to about 8.3 gigawatt. We are having 8 power plants under construction, leading to about 8.5 gigawatt. And we are also under planning phase 10 gigawatt of pump storage power plants. The presentation with this contribution, we are sharing about 16% of the total hydropower capacity installed in our country. The presentation I am sharing today is co-authored with my colleague Ms. Shubhra. This is a brief agenda of my presentation today. As we all know that India is on a fast transition to RE, and we have currently having 505 gigawatt of installed capacity, and a major portion of this is prominently rich in RE resources. About 49% of 6% of this is contributed by wind and solar power plants, and with this rapid growth, we are also facing a lot of challenges in the waste generated out of these sources. As Dr. Gurleen Kaur and Dr. Sneha has already said, that we are getting about 4 metric ton of solar PV waste by 2030, and this growth is expected to be about 200 plus metric ton by 2050. Similar is the case of the wind turbines. The growth of solid waste generated out by wind turbine blades is going to be 4 times from the current rate of 100 metric ton per year. Similarly, the major fleet of hydropower plants all over the global, about 60% of these fleet is going to be 30 to 40 years older from their installation date. So they will be soon enter into the RMU phase, or they will enter into the refurbishment cycles. So these are the few challenges which are going to face in the coming decades. So when we are moving this phase, there are certain constraints for the smooth transition into the REH energy transition. As Dr. Gurleen Kaur have already said, there is fragmented approach. There is no unified framework exists across the solar, wind, and hydropower and the PSP sector. And it is observed that most of the organizations today are following the take, make, waste model approach. The assets in the RE power plants and the other utilities, they are discarded just because of their age. We are not having any clear perspective and clear visibility about the equipment degradation, their pattern cycle, and their remaining useful life. So we just simply discard them and just items goes to the landfill items. Due to this, we are not having any efficient material recovery from out of these various waste. The waste or the recovery should not be started at an end of the cycle. It should be started during the design stage itself. We should design our RE product in such a way so that we keep our waste coming out from these products at a minimum level. The product should be durable, they should be modular, and they should be as far as repairable, and standardized items should be there. And we should try to design in such a way so that we can keep materials used and in reuse, and this is remanufacture, refurbishment, and all the process should be very easy for the end user. We are accountable to the environment also. So we regenerate our nature. We should try to keep the minimum stress on the virgin material extractions, and we should explore more and more biodegradable options so that we can recycle most of the products in an easy way. So India today is on the verge of one of the most ambitious energy transitions of the world. So as we are on the work this transition, we are relying heavily on the material extractions. So this transitions and this circularity in this energy transition will help us to be a mineral independence. We should be able to meet the climate target and SDGs. We should be able to extract more and more materials out from the recycled sources. This should make our system more resilient against these global disrupted supply chain shocks and the rising demand. And this circularity will develop ecosystem for refurbished and second life products all over the globe. There are large amount of global circular opportunity that lies in the current renewable sources. Hydropower alone is contributing to about 20 to 34 billion of circular opportunity. Solar PV panels about 8.8 billion in recoverable materials like silver and silicon, and wind energy is about 20 to 25 billion circular opportunity lies in the blade recycling and composite recovery and gearbox remanufacture and tower reuse over the time. Overall, if you see, the macro level economic impact is going to be about 4.5 trillion across the globe. With this context, there are number of advantages we are getting out of this circular framework. We are able to achieve the 15 to 20% life cycle savings throughout the circularity practices. It will facilitate 30% carbon reduction emissions via the resource optimization. And the industry should target for a 25% waste reduction in renewable energy. And this will unlock a material recovery of about 8.8 billion from solar PV materials. And this will always lead to an economic value generation for all of us. Solar PV circularity framework is not created at the end of the life cycle. It is started during the installation of the panel itself. The data shows that the 5 to 7% of the materials they break during the installation itself. So this leads to about 41 million of the broken modules in the 2021 itself. So there is a huge opportunity lies for the robust and safe packaging materials like fiber PV pellets for the packaging as a packaging items rather than the wooden pellets. When most of the 90% of the solar PV waste is going to the landfill and only currently 10% of this is going to be recycled. So there is a huge gap. And we should give a second life potential to our solar panels which are having less efficient. We should shift to those panels to our agricultural pumps and some other microgrids so that that should not go directly to the landfills. Similarly, if you talk about the wind power plants, they are having lesser life as compared to the other renewable sources, but it's a good thing that most of the parts of the wind turbines, they have high circularity rate of 80 to 85%, but only the wind blades in earlier days, they are completely going to the wind landfills, but after the UV ban on the restriction of the landfills of the wind blades, the more innovative technologies like silosis and pyrolysis came up, so that now we are able to recover the fiber and resin out of these blades. So overall, if you see the wind's energy circularity are also having a huge potential, about 20 to 25 billions. Hydropower plants are very circular in nature and they are very inherent to this. The global value shows that 95% of the materials used in the turbines, they are recoverable. They are designed in such a way that each and every component, they are replaced at site with the HUF coating and different type of techniques. We can extend the life of the hydropower plants. Moreover, if you see that after the 20 to 25 years, the hydropower plants, we need to create an extra bed dam. We just go to the RMU phase, that is renovation, moderation and operating phase, and with this life extension of 20 to 30 years without new material access takes place, we can avoid the emissions as compared to the greenfield constructions. This leads also to the capacity operating of 10 to 30% in many old power plants, and this also with the advent of the technology, improvement of the technology, we can implement the efficiency improvement of about 2 to 5% in these power plants. So this is a very good opportunity lies for us in the hydropower plants. Similarly, Government of India and CEA always form plans in regularly after 5 years for the RME of the different power plants that are entering into the RMU phase, and we're getting our best out of these RMU plants. As we are moving to the round-the-clock energy systems, NHPC has also come up with the Leh microgrid pilot project, where we have installed integrated 225 kilowatt solar power plants with 25 kilowatt solid oxide fuel cells that demonstrate circular energy loops, enabling nighttime standalone operation without diesel backup in the high altitude conditions. During the daytime, these solar panels, they used to generate hydrogen, and during the night time, we can generate the electricity out of this. So, another project of the NHPC is hydrogen mobility station installed in Chamba. The hydrogen generated during the solar power electrolysis fueled the hydrogen electric passage. This reduces the fossil fuel dependency in hilly terrain and showcases the circularity through clean and transport integration. So these are the key benefits we have already discussed in our slide. And there are certain policy recommendations for the smooth transitions, so that for this to implement the circularity in renewable sectors, we should extend the producer viability in a true sense. The manufacturers, they should come forward and should make mandatory recycling targets for PV modules, wind blades, and the components on the sales volume, and they should take the responsibility for this. The government should mandate the landfill restrictions on various RE sources coming out as a waste, and it should do a regular third-party audit so that the landfill restrictions should be actually implementing in the ground level. The circular economy-led procurement principle should be embedded in the contract document itself. The public tenders should prioritize the vendors which offer the take-back schemes and high recycling designs in their products. So overall, a national recycling cluster should be made time to time in a those areas which are reached by the RE sources. We are currently at 2025. In the next 10 to 15 years, we should scale up our infrastructure for this circular economy, and so that by that year 2040, when the first fleet of the solid waste coming out of these resources will come out of their plants, we should have a mature circular economy in place. So, circular economy is very essential for sustaining the India's rapid growth and RE expansion while minimizing resource strain. It has huge economic potential, and NHPC pilot projects in Leh and Chamba have already demonstrated a suitable circular model for circular integration in the challenging and tough environment. And these policymakers, all the stakeholders, policymakers, end users, and the manufacturers should come forward so that the circular economy should not be a concept itself, but it should integrate independently in a true manner. So I will leave the stage with this thought that circular economy is not just an environmental necessity, but a strategic imperative for the India's energy security. Thank you very much.
Thank you, Mr. Prakash, for your nice presentation. Thanks, everybody. Thank you all.